see, I want to produce a negative charge. So this plastic tube is polyethylene, and it acts like rubber, like Benjamin Franklin's rubber. I do have an actual, here it is. I do have an actual vulcanized rubber rod, which we'll be demonstrating later. So this is the same stuff as car tires. So vulcanized rubber is natural rubber, like from rubber tree plants. Rubber trees. Rubber tree plants are not rubber trees, but nonetheless, rubber trees produce something called, in its pure form, latex, and which is a white fluid. And pure latex rubber is actually kind of white or pinkish. You add some other chemicals to it, and it turns this color, and it hardens. A lot of people think it's rubber, so it bends. And how many of these things broken in half do you think I have? All except for this one, right? So that's why this does no longer go around. Oh, it's rubber. Snap. Oh, darn. Sorry. Okay. So, but this does the same thing as rubber. So this is going to produce a negative charge. The rubber steals electrons from the wool. All right. So we're looking at the difference between conductors versus insulators. Metals. What do you think? Conductor or insulator? Conductor, right. Oh, wires are made of metals, right? So it is going to be true that metals are all good conductors, relatively good conductors. And then when we compare the conductance of different metals, which is coming up, some metals are better conductors than others, but all metals conduct at least pretty well. So this is aluminum. And essentially, the deal is, if I place a charge on a conductor, that charge will be able to move across the entire conductor. It'll like be adding extra water to a swimming pool. You know, that extra water, the entire swimming pool increases by a little extra water, right? Okay, so you add don't be thinking of an Olympic pool and adding a drop of water. That's okay. Think of a kiddie pool, adding an extra gallon to the kiddie pool. That water swirls all around the kiddie pool, right? Okay, that's like adding extra electrons to a conductor. So, remind you what the fifth ball will look like when I just approach it with a net charge. Here's my land tool. Took my land tool. That's it. Yes. I hear it crackle. There we go. All right. So this is what it looks like if you approach a negative charge through the fifth ball. Oh, that was a good one. See the effect? Remember, there's an attraction, contact, repulsion. And by doing this, I will now reset the charge or neutralize or ground the fifth ball. So that should be neutral now. All right, so I'm going to put a charge, a negative charge on this end of the metal rod, and you can see what happens. And I think you saw exactly the same effect, right? Okay, there was attraction, contact, repulsion. That's due to the fact that as I put extra electrons here, those extra electrons immediately swarm throughout the entire conductor. So the electrons will move throughout the entire conductor. Throughout the entire conductor. Watch that again. Okay. All right, let's see what other substances do. So in general, we think of plastics as being insulators. This is a type of plastic called nylon. It's one of the earlier plastics developed. Now let's see if you can see anything happening here. Okay, anybody see an effect there? Did anybody see any effect at all? Okay, there was a little bit of motion, right? Just a little bit. So there was some effect, but definitely not the full effect of attraction, contact, repulsion. Now I contacted this side of the nylon. So if we turn it around, let's see if this side of the nylon has any effect. And yes, it does, in fact. You get the attraction. So that means the negative charge that I placed onto that end of the nylon stayed there. So any net charge that you place on an insulator generally stays in that location. So let's see the effect of some other plastics. This one is called polyethylene. I will have a list coming up on the board when I get to it. So polyethylene, let's see what effect polyethylene here. Have I been standing in the way of this? Have you been able to see the up there? You can't see that? Okay. Yeah, you're right there. Again, there appears to might be some effect, but is there any effect?
Not really.
Not really, but I touched this end of the polyethylene and yes, there was still a charge that was placed on the polyethylene, but it didn't move throughout the polyethylene. High density polyethylene, by the way, this is the plastic that milk jug. So that's milk jug plastic right there, all right? Here's polystyrene. When we have expanded polystyrene, that's what we call styrofoam, which is actually expanded polystyrene is what the packing peanut pit balls are made out of. So that's this stuff. That one has a little, that's supposed to, okay, yeah. All right, polystyrene, do you notice effects of polystyrene?
A little bit.
Yeah, there was a little bit. It's supposed to have been a little bit more obvious than that, but there did end up being an attraction at the other end. So, do we say polystyrene is a good conductor? No, it's still not a good conductor. But if we had to choose between polystyrene and nylon for an insulator, what would be a better choice? Nylon. Okay, nylon was a better insulator than polystyrene. So the point is, we do not have that's a conductor and that's an insulator. We have a big range of conductance and insulation. To take a quick look at other things, this is the vulcanized rubber. In other words, vulcanized rubber, this is car tire material. Okay, vulcanized rubber. Good insulator, you'd say? Yeah, that was okay. Again, in all situations, you may notice there is a little effect over there. So not everything is a perfect insulator. This is another plastic called acrylic. That's the same thing as the clear tubes are made of. This is the original plexiglass. Okay, I'm getting nothing. Let's see if the charge is still in that. Okay, yeah. The charge is still located at the place where I put it. So the charges do not move through the acrylic. Net charge is placed on the acrylic, stay at that location. So the acrylic is a good insulator. Wood. How many people, where do you think this will be? Conductor or insulator? Just guess. Insulator? Okay, let's see. Okay, I would say that's a conductor, wouldn't you? Okay, would you say it's a good conductor? No, you wouldn't say it's a good conductor. You wouldn't say it's a good insulator. That would be right in the middle. Let's not use it for either one. Okay, but we can use wood's derivative, paper. So this is raw paper. This is actually paper towel paper. Raw paper has the least amount of processing done to it. So it's pretty much just mashed up wood pulp and dried out. So paper, raw paper. Okay, that initial motion, if you saw anything, I think it was the breeze of me moving closer. That's essentially nothing, right? Paper turns out actually to be a really good insulator. That is raw paper. Processed paper, this is pink printing paper. Now, when you have highly processed paper, a lot of stuff is added to the paper to make it feel and look smoother. And then there's the pigment added to give it a color. Let's see what this does. That conducts. Okay, so not just because it's paper, you can't say, oh, that's going to be a good insulator. It depends on what you've done to the paper. All right. Now, most people will realize that metals are good conductors, and most plastics are good insulators. Some are better insulators than others.
So why, if the wood was a good, or not a good conductor, but if the wood was a conductor, why was like the raw paper not a good conductor?
Because actual wood has more in it than paper. See, paper is derived from a certain part of the wood called the cellulose. So when you create paper, you don't just take wood, chop it up, and there's paper. Yeah, it goes through several treatments, and you get the pure cellulose. And cellulose itself does not conduct electricity very well. All right. So this is glass, actual glass. Supposed to be a little bit more. Come on. There we go. Eventually got there. Glass is a pretty good conductor, and glass is pretty good insulator. And it's another case of it depends on what you've done to it. You can make lots of different types of glass. Depending on what's in it, it will be more or less insulated. Pure glass, which is just silicon dioxide, essentially sand, yellow beach sand, melted down, that's pure glass. However, pure glass, silicon dioxide, is very, very brittle and tends to shatter easily. So to make glass harder, stuff is added to it. Guess what is added to glass to make it harder? Metals. Lots of different types of metals. Depending on what metal you add to glass will determine what color you give the glass. So if you add, for example, cobalt. Anybody know what cobalt glass looks like? Beautiful blue. You add cobalt to glass, you get cobalt blue glass. That's this stuff right here. One of the nicest colors I think glass can be produced. Anyway, so the interesting is glass, pure glass itself would be a great insulator, except to harden glass, we add stuff to it. Lead is also popularly added to glass. Make it very, very clear. It's interesting. You add lead to glass, and you get what we refer to as crystal. So leaded crystal glasses, those are the fancy carved glasses you might have on somebody's shelf. You don't touch the good crystal, right? Is there a question? Oh. Okay. I'll get to a stopping point here. Right. So let's see. What we got left here is just this. This is carbon. Is carbon a metal? No, carbon is not a metal. So far, we can assume to be correct that all metals are going to act very good on the conductor side of things. This is not a metal. This is carbon graphite. This is actually my last remaining non-broken carbon rod. Okay, carbon, not a metal. Carbon, conductor or insulator? I didn't start with a neutral fifth ball, so let me neutralize this. Okay. But I think you already saw it. All right, one more time. Okay. Carbon, good conductor. Not a metal, but still a good conductor. Carbon is a very good conductor. What are you guys made of mostly? Carbon and water, right? Okay. The non-water part is all carbon. So amongst other things, you're a good conductor. All right. So anyway, we've got this is just a bar where it's a continuum. That is, things are somewhere on this chart where the top end of the chart is 100% conductive, and the bottom of the chart is 0% conductive. So at the top, if we had any substance up here, it would be a perfect conductor. It would conduct without any electric resistance whatsoever. A perfect conductor. And down here would be a perfect insulator. Now we have materials that are very, very good insulators, but there is no such thing as a perfect insulator. You can't completely stop electrons from moving. And when you think about it, it kind of makes sense. First of all, do you think a vacuum of empty space would be a good insulator? Would you think so? At first, you might think so, but then have you ever seen a spark? Guess what's happening in a spark? Those are electrons jumping a gap. If you have a perfectly empty space, well, actually, electrons will be able to jump the gap more easily. So perfect empty space, a total vacuum, not a good insulator. So they're putting stuff in the way will actually make it more insulating. Air gaps are not a good insulator for electricity. So that means you have to put stuff in between to be a good insulator. And what is all stuff made of? And what's on the outside of all stuff? Electrons are on the outside of all stuff, right? So you're using stuff made up of electrons, trying to stop the flow of electrons. At some point, it's going to break down. So as far as we know, we have no materials that are perfect insulators. We have not created any perfect insulating material. We do have materials that are very, very, very good insulators. They'd be somewhere around here on the chart. Extremely good insulators. These materials are referred to as dielectrics. Dielectric. These dielectric materials actually get, as the voltage goes up, which is to say like the electric pressure goes up, the things pushing the charges goes up, dielectrics become better insulators. So in other words, it just makes me stronger. Your hits just make me bigger and stronger. Right? That's dielectric in the electric world. We have one material, natural material, that is a dielectric. Natural material, very, very good insulator. In fact, it's probably the best insulator of all naturally available substances. And it is available pretty much everywhere. But here's the thing. It can only be an insulator if it's in its pure form, which ends up being kind of difficult to get it in its pure form. Any ideas? It's very abundant. Folks at home, any ideas? Very abundant substance. Not likely to be your first guess as an insulator. Stuff that you might think is a conductor. It is water. Water is, in its pure form, an extremely good insulator. It is a natural dielectric, which makes it an extremely good insulator. But it needs to be in a pure form. Pure water is actually a very good, it's a better insulator than any of these. But the problem is, the thing that makes water a good dielectric and therefore a good insulator also makes it something else. You know this from chemistry? Folks at home, know this one? Water is also known as the universal, chemistry people? Water will do this to everything eventually. Very quickly to stuff like salt and sugar. Yeah, water is the universal solvent, universal solvent. Water dissolves everything. Water will dissolve these plastics given enough hundreds of thousands of years. Eventually it will. It takes a long time for water to dissolve man-made plastics, but water dissolves everything. And when water dissolves stuff, that stuff that is now dissolved in water carries a current through the water. So charges will flow through the stuff that is dissolved in the water. But water itself is not going to allow charges through. So if you can get pure water acts as a very good insulator, but you have to contain the water in something, right? And water is going to start dissolving that something that is containing the water. So glass and plastics do not dissolve very quickly. So when you're using water as a dielectric resistor, it's usually in a special type of glass that does not dissolve at all. Anyway, so that getting out of the way, we do have things that are very, very good insulators. Water, one of the best, ironically, water is one of the best insulators available. And we got, we'll just make this chart right here. So pretty much near the top of the chart are most metals, very close to the top of the chart. Good conductors, but not perfect conductors. The plastics such as polystyrene, polyethylene, nylon, one of the better ones, glass, got there, acrylic down here, vulcanized rubber. Processed paper is not a good insulator. It's more on the conducting side of things. Raw paper is closer down here. Wood is nearly a conductor. And carbon graphite is right up there with metals. For metallic conductors, I'm going to go through the top four. I'm going to remind you. That which makes metals good conductors of electricity is the same thing that makes metals good conductors of heat. And it's the same thing that makes metals shiny. So therefore, and those are, by the way, I'll get back to these. They're known as free electrons. These are electrons that are not bound to any particular nucleus. They're just free to roam around. I'll get back to, I was going to do that earlier. I forgot to. Okay, but anyway, it's the same thing that makes metals shiny, which makes metals good conductor of electricity, good conductors of heat. The same thing, free electrons, non-bound electrons. So therefore, the shiniest of all metals should be the best conductor of all metals. So what is the shiniest of all metals? I think I did this before. It is silver. Silver is first place. Olympics have it wrong. Silver has the best conductance of all material, all metallic materials. Now this is closely followed by just as shiny, but a little bit more colorful. And for some reason, people say, I like that a lot more, right? What's number two? Give you a hint. Shiny metals make them precious metals. So what are the precious metals? Gold is number two, right? Gold is second place. See, Olympics have it wrong. Now, number three is not platinum. Okay. Number three also is a precious metal. And if you look on a periodic table, look on the periodic table. Okay, there's one over there, one over there. Can you find silver and gold? Ag and Au. Silver, Ag is silver, Au is gold. Copper. What's in the same column? Copper. Then copper is number three. So it's if you look at the periodic table, you see that it's copper, silver, gold in the same group of the periodic chart. And they're in the same group because at that point in the group, this is where electrons are the most or least bound, the most loosely bound to the particular nucleus, which means it has more electrons that can roam freely. And those are the ones that carry the current. Okay, after copper, for some reason, it skips over to to aluminum. Number four is aluminum. And then after aluminum, it's a mad dash for fifth place. So it's pretty much a tie, an 18-way tie for fifth place. And again, the shinier the material. Silver is very shiny as long as you polish it. Gold does not react so quickly to oxygen, so gold does not need to be shined up so often. Silver really reacts quickly, so you get a tarnish on silver. And once you get to silver oxide is neither shiny nor conductive. So there's a lot of metals that once their outside oxidizes, that oxidized layer prevents the conduction of electricity. How much time we got? 55. Okay, still on track here. All righty, so that is conductors. All right, so I already said that there's no such thing as a perfect insulator. What about the other end? Is there such a thing as a perfect conductor? What would you think?
No.
Okay, but can I have you think again?
Yes.
Okay, it is true. There has been no development of a perfect insulator. That seems to be not possible. But we do have stuff that is referred to as superconductors. Materials called superconductors occupy that 100% line on that chart. Superconductors exist. They've existed since the 1960s. They are completely people-made material, right? They do not exist in nature. We actually pull a little quantum trick on substance. We trick gonna get a little technical on you, but we trick fermions into believing that they're bosons, roughly. So objects with 1/2 integer spins are tricked into believing that they have 0 integer spins, and they start behaving more wave-like rather than particle-like. No, you don't need to know that. That's fine. Just got a little quantum at you. You have to do that every now and then. All right, but nonetheless. Superconductors exist. They are people-made materials. They are not metals. They can't be metals. But not only do they exist, they conduct perfectly. Without any electric resistance. It gives them absolutely mind-blowing qualities. Have you heard of things called maglev trains?
Yes.
Magnetic levitation. Magnetic levitation is done through superconductivity. We can create trains that literally float over the track that they're on. However, to do this, there has to be one of the two connection points needs to be superconducting. But the problem is, why do we have it everywhere? The problem is superconduction only works at extremely low temperatures. So think of cold and you're not even close, all right? Think of much, much colder than that. Oh my goodness, Antarctica, -80 degrees Fahrenheit, not cold enough. We have to get down to the temperature of liquid nitrogen on the order of 77 Kelvin, which is about 200 degrees below 0 Celsius. And that makes it about 340 degrees below 0 Fahrenheit. So we're talking about extremely, extremely cold temperatures. So on the order of 200 degrees, 200 degrees Celsius, which is about -320 degrees below 0 Fahrenheit. These are chilly temperatures that do not exist on Earth normally. So it's very difficult and very energy consuming to produce temperatures that low. How cold does your freezer get? 20 below maybe, right? If you got a good freezer, that gets to 20 below. Okay, how cold does it get outside during the worst winter in New England when it hasn't been in for a while? What's that? Maybe -20, maybe -40 if you're on top of Mount Washington on a particularly bad day, which, by the way, I was one winter. -40, I experienced -40. That's no fun. Anyway, nothing. Antarctica gets down to -80 Fahrenheit, still not even close to the temperatures required to make superconductivity work. All right, so superconductors do exist. It is actually a very, very active field of research trying to make what they call warm superconductors. A warm superconductor would be one that worked at merely 100 degrees below 0 Fahrenheit. All right, so we're working on that. We have raised the temperature of superconductivity, but not to the point that we can make it a practical application yet. It's still very difficult to get things cold enough to be superconductors. But the point is, they exist, and it's a technical problem, not a theoretical problem. That means we could surmount that. We could have so-called warm superconductors. It's still a field of study right now. People are working on it at this moment. All right, so going back to the chart, we have, yes, way up here, we have superconductors. Last thing for the day, materials called semiconductors. You've heard of them, right? No?
Yeah.
Semiconductors. Where are semiconductors used? In what technology are semiconductors used? All technology. All technology uses semiconductors. Anything that is computer processed, which is everything, including your toaster now, right? Computer processing, what do they use? Material known as semiconductor. What is computer language? You know this. Computer language is all based on what two numbers?
1 and 2.
1 and zeros, which stand for on and off. 1 is on, 0 is off. A semiconductor is that on and or off. Semiconductors can either be a conductor or an insulator, depending on circumstances, which we can engineer. That is, the same thing can be switched between being a conductor or an insulator, between being on, 1, or 0, off. All right, so semiconductors can either be conductors or insulators. And the point is they can switch between being one or the other. So semiconductors switch between conducting. I can't spell today. Conducting and insulate, insulate. So the point is they can switch back and forth. A semiconductor can switch between being on, 1, or off, 0. Now, there's two main materials that semiconductors are made from. And that is silicon and germanium. If you look on the chart, you'll see silicon and germanium are in the same group again. Silicon is just above germanium. Silicon's right underneath carbon. So it goes carbon, silicon, germanium. You can see the charts. You set a class. Technically, carbon can be turned into a semiconductor, but it's more labor intensive. Silicon and germanium work much better as semiconductors. They cannot be pure silicon and pure germanium. We have to add other stuff to them. And depending on how we add it, makes it a different type of semiconductor. So these are the semiconducting elements, the best semiconducting elements. And we're just going to refer to the two types of semiconductors. We have transistors. Transistors are the ones and zeros of all computer, all integrated circuit language. Transistor can be switched between on and off. In other words, a transistor changes from a 1 or a 0, depending on where it is in the computer chip. The transistors inside computer chips are the ons and offs. They are the ones and zeros of all computer languages. So without these, we have no computers, none, or anything that does any kind of computation. No calculators, no watches, no phones, cars these days. The other main type of semiconductor is known as the diode. And a diode is like a one-way street for electricity. If electrons try to go in one direction, it's on and they can go through. Electrons try to go through in the opposite direction, they can't, it's off. So it's a one-way valve for electrons. A lot of people want to say that a semiconductor is somewhere here in the middle. No, anything in the middle here is just not a good conductor and not a good insulator. It's somewhere like wood. No, it's better than metal for insulation, but it's still not good either one. A semiconductor is specifically, switches between being a good conductor and a good insulator. And you have to take an engineering course to learn more about transistors there.